Within this video, we're going to start discussing ideas within Chapter 5. That's where we look much more deeply at the concept of energy. So within this video, we're going to try to make sense of some ideas right at the start. These are, I'd say, largely conceptual, and it's ones where I think you're really going to have to pay attention within this video and think along the way. If we get a good sense of those, then we'll be able to apply them in the other parts of the chapter, which are more doing calculations. But I find most of the time students have challenges right here understanding these terms and being careful with the ideas. So that's the purpose of this video. So we're going to be making sense of these different concepts: heat, work, potential energy, kinetic energy, internal energy, and temperature. And I showed the symbols there. Heat will be given symbol Q, work W, potential energy, kinetic energy, internal energy will be E, and then finally our temperature. We've already begun to make some sense of this. Earlier we saw that we can relate the kinetic energy and the temperature. Where the average kinetic energy of our particles moving through space, that's what the temperature was measuring. Let's look at that at the particle level. So I begin with O2 as a solid. Notice how the particles are in motion. If we're adding heat, we can begin to adjust that motion. If we look at different phases, like a liquid or a gas, if I observe the thermometer, the temperature was different. Even for a gas, though, I can raise the temperature and I can increase the average kinetic energy of those particles. Let's switch to H2O. We're taking it down to a very low temperature, but it's still in motion. There's still some motion with the particles. Greater motion with the liquid, and even higher temperature with the gas. Once again, the temperature is describing the average kinetic energy of these particles as they're moving through space. And we saw that by adding or removing heat, that was symbol Q, we could change this motion. So let's move on from there. First of all, then, considering the energy associated with chemical reactions. Our unit of energy is going to be called the joule. Here I am doing a demonstration exploding a hydrogen-oxygen balloon in class. Kaboom, great explosion. That produces about 13 kilojoules of energy. So I think that we're going to typically be seeing units of energy in either joules or kilojoules. And clearly energy is involved with this chemical reaction. Tremendous kaboom. So initial thought for you, initial thing to consider. So heat's given off when this hydrogen burns in air according to the equation. Which of the following is responsible for the heat? Where is this heat energy coming from? What I'd like you to do is pause, tell me what your answer is. A, B, C, D, E. When I do this great explosion, kaboom, which of the following is responsible for the heat? Take a second and give me that answer. Now, heat's also involved, energy is also involved in physical changes. So I'm going with H2O because I think you're familiar with its substance in different states. Melting would be an example where we're adding energy to go from a solid to a liquid. Boiling, adding energy to go from a liquid to a gas. If we're going in the other direction, that's called condensation. If we're going from a gas to a liquid, that would involve removing energy. So energy is crucially important for understanding our chemical changes and our physical changes. Our analysis of matter, it's nothing if we don't also consider energy. How about this example? So if I have water at 100 degrees C, have it on the stove in the kitchen, I see it starts to boil. I would say at the same time, the gas is also at 100 degrees C. If I have my thermometer right there in the top of the water, or right above it in the water vapor, in both cases, it boils at 100 degrees C. It transforms from the liquid to the gas. So a couple insights there. First of all, I'd say then they both have the same average kinetic energy because they have the same temperature. So a solid and a liquid at the same temperature, they have the same average kinetic energy. My liquid and the gas at the same temperature, they have the same average kinetic energy because that's what the temperature is telling me. What's different? The potential energy. The position of the molecules is certainly different if I consider the water or where they're more spread out as a gas. Students generally have a much better sense of the kinetic energy My point now is we've got to understand the potential energy. So in order to do that, we're going to explore a skater on a frictionless track. What I want you to do within this video is, first of all, observe the motion of the skater and connect that to these bar graphs that are showing relationships between the kinetic energy and the potential energy. So bring together those ideas: location of the skater, potential energy, and kinetic energy. In a sense, match up these bar graphs with where they go. So let me hop over to our simulation. Here's the skater. Frictionless track. He's going to keep going and going and going. Watch it for a long time. He never stops. I want you to make sense of his position, the kinetic energy, and potential energy. Okay. So if I go back within it, this is how I would match it up. I saw that when he reaches the peak, there's a pause. Kinetic energy went down to 0 as his motion stopped, and the potential energy was at the maximum. As he was descending, I see then the kinetic energy is going up, the potential energy is going down, and at the bottom there, he was all kinetic energy, no potential energy. One thought within here, notice in this case, the image shows 0 potential energy. If we go back to our simulation, it's not going down to 0 potential energy. Why do you think that is? I think it's because he's still above the ground in this setup. If I'm calling this bottom here 0 potential energy, he's not at 0 potential energy. It comes down to what I am calling the reference value. The potential energy right now, if we say the reference is when he's all the way down at the ground, he's not all the way down at the ground. Now, notice his motion. If I change the reference to be the bottom of his track, still the same motion, but now within our setup, we would say the potential energy is going down to 0. My point being, the choice of the reference is very important. It doesn't change his motion, it just changes what we are calling 0 potential energy. What's going to happen if I put this line halfway up and down the track? Will that change its motion? It doesn't change its motion at all, but now it's given me values that I would consider to be negative energy. Relative to that 0, the potential energy is increasing or decreasing, but the sign is different because of where I'm calling the reference. In this class, we're going to end up describing the reference as when there is a large separation. A large separation between the particles that are being attracted to each other. So in this class, we're going to be dealing with negative potential energies quite frequently. Couple takeaways then from this video. First of all, the potential energy is lowest when the particles of matter are attracted to each other and they are close together. That was true with the skater. Higher potential energy when the separation was greater, lower potential energy when they came together. Second is we need to know where we are defining the reference value of potential energy equal to 0. If we set it so that means a large separation, negative potential energy is going to be certainly possible. So within this case, if we set the reference here at the bottom, potential energy at the minimum was 0. If we set the potential energy, so a large separation is 0, then as the potential energy goes down, it gets more negative. This is how we're going to sort of explore it here in the chemistry context. Potential energy has to do with the position, the forces of attraction or repulsion we have based on their location. And in this class, what's going to lead to that is the fact that matter, our particles, are charged. In skate park, it had to do with gravity. In our case, particles of matter are too small to be affected by gravity. The mass is too small. But they carry charges. So here's our expression describing that. The calculation involves the charge of one particle and the charge of the other and their distance. So we have a net attraction when one is positive and one is negative. Notice my math, and that leads to a negative potential energy. What does that mean graphically? We're going to define our zero once again as when they are far apart. As they move closer together, potential energy is going down and it's becoming more negative. What if the charges were the same, both positive or both negative? In that case, when they're large apart, the potential energy would be closer to zero, but as they move closer together, we would see in this case the potential energy is going up. They now have the potential to move apart. One way that I sort of try to demonstrate this is imagine you got in each hand right now a magnet. Put a magnet in each hand. Physically do that, all right? Hold your two fists together. Now feel the force of attraction as they get drawn together. As they get pulled together, you're having them come closer and they're moving to lower potential energy. It's going to take work to separate them, so push and separate them apart. Now you've raised the potential energy. We're going to call that, when they're farther apart, a value of 0. Now take one in your hands and try to turn it over so now the magnets would be repelling each other. You can try to squish them together. You could do work to try to squish them together, but as soon as you let that go, boom, they're going to come right back apart. In this class, we're going to be thinking time and again about matter when it's attracted to other matter. So on this bottom part of this figure, we're going to be in that space quite a bit. We don't have to worry about the math part, but we do want to make sense of the sign and what it's telling us. I find that it helps a lot to think about the sign on sort of like a number line. The values, when they become more and more positive or move towards the positive, that means they're moving to a higher potential energy. When they move more and more down this part, more and more negative, they're moving to a lower potential energy. Our 0 is defined where there's a large separation. But as they move more and more negative, the potential energy is getting smaller and smaller and smaller. Negative 100 is smaller than negative 10. It's even more negative. It's an even lower potential energy. This part right here, thinking on a number line, I find is a really important idea for us. Let's connect it now to a little bit of chemistry. So let's say we've got these ions that are far apart. There's an attraction, but they're farther apart. It's describing that as a higher potential energy. As they come together, the ions are moving together, a lower potential energy. There was an attraction, and they move closer together. Just like on skate park, when the skater moved closer to the earth. They've moved to a more negative value. That's a lower potential energy. They're more stuck together. When the particles of matter are stuck together, they have a lower potential energy than when they were apart. It's going to take energy to move them apart and increase the potential energy, just like it took energy to separate those magnets that you had in your hands. So an implication of this, it's going to always take energy to break a bond. The atoms are stuck together at a lower potential energy when they're bonded together. It's going to take energy to separate those and move them to a higher potential energy. Conversely, forming a bond always releases energy. You're moving from a higher potential energy to a lower potential energy. That energy is not lost. It can result in kinetic energy. So this picture right here, this might be different than how you answered our initial question. So pause a second. Does this make sense in the way that we've been trying to explore potential energy? Think about your initial answer in terms of bond forming and breaking and what it meant when I did an explosion. Share your ideas with me. Now, this idea of looking at the energy, we want to now add to it, what are we talking about the energy of? The system or the surroundings? The system, that is the thing that we're studying. So that might be the beaker, that might be the container of some kind. That's what we're studying. The surroundings is everything else outside of that in the universe. There's different kinds of systems that we could discuss. Isolated means the energy and matter can't be exchanged with the surroundings. Closed, the energy can come and go, but not the matter. And open, they can both come and go. So take a second, see if you can match these up. Which of these do you think is best describing isolated, closed, and open? So the open would be like this pot that I have on the stove. I can add energy, I could add heat, I could turn on the stove, matter could come or go, I could pour more water in, it could evaporate, it could boil away. This thermos is trying to demonstrate an isolated one. The energy and matter, whatever stays inside, is initial inside, stays inside. This other one here might seem a little bit odd, but it was the one we are left with. This is a piston. Matter is clearly stuck on the inside, but what does it mean to say energy can be exchanged with this? What is the role of the piston? We're going to explore that. Now, the first law of thermodynamics, we're just going to see that the total energy for an isolated system is conserved, stays constant. What are sort of the implications of that? We're going to add some ideas to it. Let's begin within here with considering what internal energy is. So if we have the particles of matter, they're all moving around, the internal energy is all of the potential energy and kinetic energy put together. There's this idea that we generally don't know a numerical value for the internal energy. Let me demonstrate what that's talking about. So let's add some particles to our box here. They clearly have kinetic energy as they're all moving and bouncing around. If there's attractions between them as well, there's going to be potential energy. So this is a very complex circumstance. I mean, I guess I could pause it and see all of their positions and look at all of their relationships with each other, but I'm not really even pausing it, right? They're going to be in motion because they have kinetic energy. So the idea is the internal energy would be the sum of all of the potential and kinetic energies. Instead of worrying about measuring that, what we're interested in is how we change the internal energy. How much heat have we added that changes this overall kinetic and potential energy, or the heat that we've removed as we've cooled it. We're interested in the change on that. When we do the math on that, we're interested in the change in internal energy by considering the final minus the initial states. In this chapter, we frequently would do those kind of calculations. Delta, the change, is considered as the final minus the initial. If we were to consider the internal energy here, so I show O2 solid at 31 K, O2 gas at 194. Which of these has a higher kinetic energy? Which has a higher potential energy? And which would you say has the greater internal energy? Tell me what you're seeing on that. I think the O2 gas has the higher kinetic energy because I'm going to look at the temperature. Higher temperature, higher kinetic energy. How about higher potential energy? I think it also has a higher potential energy. The particles are more spread out. So I think that the O2 gas at 194 in this comparison definitely has the greater internal energy. It's lower for the solid at a lower temperature, higher for the gas at the higher temperature. In order to go from the solid to the gas, I would have to add energy. And notice my math here. If I'm considering the final minus the initial, when I add energy there, it would have a positive value. So in terms of adding energy to go from a lower to a higher internal energy value, that has a positive value. If I was going in the opposite direction, from O2 gas at 194 to the solid at 31, the value would be negative. So we need to make sense of the sign there. We're generally interested then in the change, which is the final minus the initial state. We're going to see that we can change it in two different ways. We can change the internal energy, remember our symbols, due to the heat and the work. The heat one I think might be easier to understand. So Q is our symbol for heat. Heat can go into the system from the surroundings, or it can go out of the system into the surroundings. So when the value is positive, we call that endothermic. Heat is going into the system. When it's going in the other direction, heat's going into the surroundings, negative sign, that's called exothermic. When I do this explosion right here, kaboom, okay, this is a great example of exothermic. It's leaving the system, which was the balloon, and going into the rest of the universe, the surroundings, with the explosion. Explosions, definitely exothermic. The sign of Q is negative. What about the work? W is our symbol for work. We're interested in what is called pressure volume work, or PV work. The sign conventions, we can make sense of it back with the same way that we made sense of with the Q. When the value is positive, that means work is going into the system. When it's negative, work is going into the surroundings. So it has that same kind of directional dependence. What does it mean to say work is going into the system or into the surroundings? The volume is a great way to get that idea. When the volume decreases for the system, when we're squishing it smaller, we're doing work on it. Let me give you a demonstration for that. So notice right here, particles of matter are moving around. If I add heat, I'm going to change the temperature. I'm changing the internal energy by adding or removing heat. Okay? Now watch the thermometer right here. I'm not going to touch this heat or temperature control at all, the heat control at all. Instead, I'm going to squish the box smaller. I'm going to be changing the volume. Watch the temperature. It went up. I wasn't adjusting the heat at all, but I increased the kinetic energy by squishing the volume smaller. I did work on it. That's what it means to say that when the volume of the system decreases, I'm doing work on it. That's another way to increase the internal energy. And that's why we think about pistons oftentimes in this chapter. A piston can lead to a volume change. And what we are seeing now, a change in volume is a way to do PV work and change the internal energy. Here's a figure from the e-text describing this kind of scenario. Notice they have it set up so the reaction can take place in this part of the vessel, and then they have a piston at the top. And if the reaction takes place, this is a redox reaction, it produces H2 gas. Notice that gas now bubbles and pushes the piston further out. I would say in this case, the volume of the system is increasing as a piston got pushed outward. In this case, it's doing PV work on the surroundings. So the sign of work in this case would be negative. This is when the system does work on its surroundings. So we've done a lot now within here of trying to make sense of internal energy as being a combination of potential and kinetic, that the internal energy can be changed then by both heat and work. And we have sign conventions. Endothermic meant the heat Q was positive. Exothermic meant the Q value was negative. And finally, we made sense then of those sign conventions, whether we were talking about heat, work, or the change in internal energy. A lot of ideas to get set and straight as we move forward. You might find within this one, you've got to rewatch and re-engage with aspects in this video once again. But having that solid understanding is really going to set up as we move to the rest of the chapter.